Okay, so next for sp hybrids, these involve a lot of triple bonds. In an sp hybrid, it involves one s orbital and one p orbital. That makes a total of 2 orbitals. And that would be 2 electron groups on the central atom. And that means linear electron geometry. So if we look at carbon, a common compound that has this type of hybridization is acetylene. It burns very hot, so it's used in things like acetylene torches. And it has the formula C2H2, but if you do a Lewis structure on it, you find that it has a triple bond between the carbons. That's the only way to get an octet around both of the carbons and to have everybody be happy. And so if you look at the carbon, you have the 2 p orbitals and the 2 s orbital, and carbon is 2s2, 2p2 for its valence shell. And it hybridizes into an sp hybrid, and then you also have the original 2p orbitals. And each of those orbitals has 1 electron in it. Okay, so each carbon has 4 half-filled orbitals. One for bonding to the hydrogen, and 3 for bonding to the other carbon. And a triple bond is actually made up of 1 sigma bond and 2 pi bonds. There is a diagram on page 427 in which you can see the acetylene molecule in all of its glory. And you can see the carbon and carbon on each end. And the carbon forms a simple sigma bond between a p orbital of the carbon and an s orbital of the hydrogen, and the same on the opposite end. The carbons also form a sigma bond with each other through the end-to-end overlap of the purple-colored p orbital on the carbons. And you have 2 pi-type orbitals also, which form from the overlap of d orbitals on the adjacent carbons. One of the p orbitals would be basically going this way, on the plane of the paper, and that pi bond would be made up of the lobe on top and the lobe on the bottom. That's 1 pi bond. The other pi bond is perpendicular to that pi bond, so basically going into and out of the page, and that consists of this lobe and the lobe behind that you can't really see. That's another pi bond. So the 2 pi bonds between the carbons are essentially perpendicular to each other. So there's 1 pi bond, and here's the other one, and they're sort of like that. So there's your sigma and your pi and your other pi, and that's your triple bond. Okay, so we have the last 2 types of hybrid orbital. One of them is sp3d, or dsp3 as it's sometimes called. And as you can see here, you've got 1, 2, 3, 4, 5 orbitals involved. On the central atom. And that means 5 electron groups on the central atom. And that means trigonal bipyramid electron geometry. Okay, so for the sp3d2, you've got 3 d orbitals, 3 p orbitals, and 3 s orbital. And you have the s, all 3 p's, and one of the d's. And they will combine into the sp3d hybrid orbitals, leaving you with 4 conventional 3d orbitals. And an example of that would be arsenic pentafluoride. There's a diagram of this on page 428, and somewhat surprisingly, the diagram is actually simpler than it was for the last example of hybridization, because we're not dealing with double or triple bonds anymore. You've got the arsenic at the center of the molecule, and you can see it's trigonal bipyramid in its shape. The gold part is the arsenic, and it's forming sigma bonds with the p orbitals in the fluorines around it. And there's the dsp3 or sp3d hybrid orbital itself. Now, keep in mind that when we say trigonal bipyramid, we're talking about the electron geometry. If there are no lone pairs on the central atom, then the molecular geometry is also trigonal bipyramid. But there could be a lone pair on the central atom, and you would still have trigonal bipyramid electron geometry, but the molecular geometry would be known as the seesaw, remember, because it goes like that. It's possible that there could be 2 lone pairs on the central atom. Remember that the second lone pair, well, actually the first lone pair, will go in an axial position in trigonal bipyramid. The axial position would be the plane that has 3 groups of electrons in it. So that's basically this plane here. The second one will also go in an axial position, and that leaves you with trigonal bipyramid electron geometry, but T-shaped for the molecular geometry. And if there's a third lone pair of electrons out of the 5 electron groups total, that would still be trigonal bipyramid for the electron geometry, but linear for the molecular geometry, with 3 lone pairs on the central atom. Okay, so those are the possibilities. All of those would involve sp3d type hybridization. The next one is the last one, and that's sp3d2. There are others, but these are the important ones anyway. Also sometimes called D2sp3. This is the type of hybridization that involves the 3s orbital, all 3 3p orbitals, and 2 of the 3d orbitals. So you end up with 6, 2, 3, 4, 5, 6 hybrid orbitals and 3 unhybridized 3d orbitals. As you can see from the name, 1, 2, 3, 4, 5, 6. There are 6 orbitals involved here. That means there are 6 electron groups on the central atom. And that means the electron geometry is octahedral. Okay, so the octahedral electron geometry. You can look at the diagram on page 428 in the book. It's actually pretty straightforward. It's very similar to the last diagram we looked at. Here you can see the central atom, SF6 is an example of this type of molecule. You can see the octahedral, the green octahedral hybrid orbitals for the sulfur in the center, forming sigma bonds with the p orbitals of the fluorines around it. And this is what it would look like in person. Remember that the molecular geometry would also be octahedral if all of the electron groups are involved in bonding. But if there is a lone pair on the central atom, any one of these positions could be the lone pair, because remember, all of the positions in an octahedral shape are equivalent to each other. So if there is a lone pair on the central atom, we would still have an octahedral electron geometry, but the molecular geometry would be what's left now, which is a square pyramid. Notice it's four-sided, and if you fill in the sides, you get a pyramid. If there were a second lone pair of electrons in this geometry, it would go directly across from the first lone pair to get as far away from it as possible, and you would still have an octahedral electron geometry, but the molecular geometry would be square planar. That is, square and flat. If you had a third lone pair of electrons, well, I guess it doesn't matter where it goes right now, so it would go here, and you would end up with T-shaped molecule, even though the electron geometry is still octahedral, because you've still got 8 pairs of electrons on the central atom. And if there were a fourth one, you could actually even end up conceivably with a linear molecule or linear molecular geometry, even though, again, the electron geometry would still be octahedral in this example. Okay, so that actually is the end of hybridization. And we can move on to chapter 5, actually. We're going back and covering chapter 5 now, because actually it makes more sense to cover that at this point than before. Yeah, I'll keep going because we're only at about 12.5 minutes for this segment of the lecture. And so I'll introduce chapter 5. Chapter 5 is about gases. And it made more sense to get some other of the preliminary stuff out of the way before we cover gases in detail. I'm going to start out by writing probably the most important thing about gases right at the beginning. And that is that for gases, under most conditions, there are no intermolecular attractions or repulsions between the particles in a gas. That is the reason, ultimately, for all of the properties of gases that we went over back when we talked about the phases of matter. You know, what are the things that distinguish solids from liquids and liquids from gases, and so on. We mentioned a bunch of different properties for gases, and ultimately all of them come back to the fact that there normally are no intermolecular attractions or repulsions for gas particles. That is, the particles that make up a gas are not attracted to each other at all, and they're not repelled from each other either. Even when they hit each other directly, they just bounce off and go in different directions, but they don't actually stop until they actually hit each other. Okay, so that is responsible for a lot of the things that we find in gases. That means that there's nothing holding the particles back. The particles in a gas have more or less total freedom of movement. And that means not only vibrational movement, which all particles have. You know, in solids and liquids, particles can vibrate in place because of thermal energy. And in fact, all particles will be vibrating at any temperature above absolute zero. So gas particles do that. But they also, gas particles also have translational freedom of movement. And that's something that particles in solids don't have, and particles in liquids have in a very limited way, and that is the ability to move from one place to another, to move around and past other particles, to get, you know, somewhere else. It is translational freedom of movement. And gases have that in abundance. Gas particles move at a high rate of speed. And that's not only because they have nothing holding them back, but also because they tend to be very small. And so it doesn't take much thermal energy to get them moving quickly. They will eventually strike something. What they strike could be another particle, or it could be the wall of the container, or us, or something like that. And when they do hit something, they tend to bounce off and just move in a different direction at a high rate of speed. But when they do hit something, they do impart a certain force or exert a certain force on anything they hit. And the amount of force that they exert when they hit something depends on several things. Size of the particle, and that depends on what gas particle it is. The speed, which is related not only to its size, but also to temperature. And also to the number of particles, because the more particles you have, the more collisions you're going to have. Okay, and the total amount of force that's exerted by gas particles striking a surface over a given area of that surface is known as pressure. And so pressure is just the amount of force divided by the amount of area. And if you think of pressure units, one of the more the familiar units for pressure might be pounds per square inch, because those are the units we usually use for things like filling our tires. And pounds per square inch is directly a unit of force per unit of area. So when you fill up your tires to a pressure of 30 pounds per square inch, what it says is that the particles of air, which are made up mostly of nitrogen and oxygen molecules, bouncing around inside the tire, are exerting a total pressure of 30 pounds for each square inch of the inside of the tire. And so if you took that pressure and multiplied by the number of square inches for the inside surface of the tire, you could get the total pressure that's being exerted on the inside of the tire. But the nice thing about force per unit of area is that you don't have to know the total area. You can just take one little, a square of that area and say how much pressure is being exerted here. And you can usually scale that up to the entire thing if you want to. But anyway, pounds per square inch would be directly a unit of force per unit of area. So looking at units, most units don't give force per unit area directly. Because as it turns out, the amount of force being exerted by gas collisions per unit of area on the surface of things that the gas particles are striking is a pretty simple, straightforward concept, but it's not all that easy to measure directly. And so we often use devices that will measure some property that represents pressure. And a good example of that is the mercury barometer. The mercury barometer measures pressure in the height of a column of mercury in a glass tube. The concept of the mercury barometer is actually pretty simple. All you have to do is take a reservoir full of mercury and a glass tube that's closed on one end, and you fill that tube up with mercury and put your finger over the open end, and then you turn the tube upside down and put the open end under the surface of the mercury in the reservoir. And you'll notice that when you do that, you take your finger off the open end of the tube, the level of the mercury in the tube will drop a little bit. And what you have at the top of the tube will be a vacuum, and the rest of the tube will be filled with mercury. And the way the mercury barometer works is that the air pressure will press down on the surface of the mercury, and the higher the air pressure is, the more mercury it forces up into the tube, and the higher the column of mercury will be. And all you have to do is measure the height of the mercury in the column, and that will represent the pressure of the air. If the pressure of the air drops, then the pressure on the surface of the mercury drops, and that allows some of the mercury to come back down out of the tube, and the height of the mercury column drops. Okay, the height of the column is very easy to measure. The reason we use mercury is that it has a very high density, and a column of mercury that represents the average atmospheric pressure at sea level is only about 30 inches high. If you were to use some other liquid like water, you know, a less dense liquid like water, then you would need a column that's something like 30 feet high rather than 30 inches. And so that's why they use a really dense liquid like mercury. Also, mercury makes it so that relatively small changes in atmospheric pressure will result in relatively large changes in the height of the column of mercury. So it's easy to measure changes in the weather by measuring the column of mercury. It's, you know, measuring its height. Okay, so all you have to do again is measure the height of the column of mercury. And the average atmospheric pressure at sea level is an important concept in dealing with gases, because that's often used as sort of a benchmark for pressures. That's known as 1 atmosphere, or 1 ATM. And the relationship between 1 atmosphere and other units of pressure would be as follows. 1 atmosphere would be equivalent in a mercury barometer. 1 atmosphere of pressure, that is the average atmospheric pressure at any given moment at sea level would be equivalent to a column of mercury that's 760 millimeters tall. So we call that 760 millimeters of mercury. The millimeter of mercury is also known as the torr. Torr is just short for Torricelli, which is the name of the guy who invented the mercury barometer. If you were to measure the height of the column in inches instead, you would get 29.92 as the height of the column at average atmospheric pressure at sea level. And it just turns out that in metric conversions for height, 760 millimeters happens to be equivalent to 29.92 inches. So it's not anything exotic. You're just measuring the height of the column of mercury. There is also the unit of pounds per square inch, which I mentioned before. That literally gives force per unit of area. And sometimes it's called PSI, sometimes it's written as pounds over square inches. 1 atmosphere, that is average atmospheric pressure at sea level, would be equivalent to 14.7 pounds per square inch. Also, 1 atmosphere would be equivalent to 101,325 pascals, abbreviated PA. The pascal is the official SI unit for pressure because in the SI system, the unit for force is newtons and the unit for area is square meters. So 1 pascal is 1 newton per square meter. And it takes 101,325 newtons per square meter to be equivalent to 1 atmosphere. We don't actually use pascals very often for pressure, oddly enough, because most of the equations that we use for pressures in dealing with gases actually call for the atmosphere, or for the pressure to be in units of atmospheres rather than pascals. Since pascals are a metric unit, you can use metric prefixes with pascals. And so 101,325 pascals would be equivalent to 101.325 kilopascals, or kPa. And I could take a couple of minutes now before the end of the lecture and do some unit conversions from one unit to another for pressures. So say a typical car tire would be inflated to 30 pounds per square inch, but that is over and above atmospheric pressure. So, you know, when you look at a tire gauge, when it's not connected to the tire, it normally reads 0, even though the atmosphere around you is exerting a certain amount of pressure. The pressure gauge for the tire is really only interested in how much pressure is inside the tire. It doesn't really care how much pressure is outside the tire. And so they count atmospheric pressure as being 0. And when you measure 30 psi, you're just measuring the pressure in the tire over and above atmospheric pressure. But that means that the total pressure in the tire is actually 30 psi plus atmospheric pressure. atmospheric pressure is about 15 psi, so we'll call the pressure in the tire 45 psi. And so what would 45 psi be in units of, let's see what we have here, torr, inches of mercury, pascals, and atmospheres. Okay, so actually, since we have this nice list up here of what everything is related to 1 atmosphere, of this list, it would probably make sense to find it in this pressure in atmospheres first. Okay, so 45 psi, and there's 1 atmosphere for every 14.7 psi. And that lands us with a pressure of 3.06 atmospheres. So the pressure inside the car tire is about 3 times atmospheric pressure. Well, if that pressure is 3.06 atmospheres, and we want to know what it is in torr, well, let's see, torr, 760 torr for every 1 atmosphere. Okay, so 3.06 times 760 is 2326 torr. Let's see, what's next? Inches of mercury. Again, if it's 3.06 atmospheres, and we know that there's 29.92 inches of mercury for every atmosphere. Uh, 3.06 times 29.92 is 91.56 inches of mercury. Okay, and then pascals. 3.06 atmospheres, and there's 101,325 pascals for every 1 atmosphere. So 3.06 times 101,325. And we got 310,055 pascals. I'm not being really careful with significant figures here, as you may have noticed. I'm just sort of showing you, how the unit conversions can be done. This would be equivalent to 310.055 kilopascals, if you wanted to use that. And well, that anyway is an example of some unit conversions. I'm going to stop there because it's 30 minutes now, and as I said, for the rest of the semester, or at least for the time being, I'm going to try doing only 3 segments per video, and at least until I can tell whether we're going to get behind, because we're so far ahead on the lectures. And so I think we can sort of shorten the lectures down a bit, and hopefully one won't get behind. So for the next few days anyway, there'll only be 3 sections. And so this will be the end for today. And we'll pick up with some more examples next time. Okay, so I'll see you then.